speaking here. So I'm going to be talking about a certain nice type of projective structure on compact manifolds. So I'm going to do a little background and context first so that we get comfortable with the type of structure we're talking about, and then I want to show you a nice result and maybe describe why it's useful. So section 1 is background and context. So I want to start with a definition. So the model spaces that we're going to be working with are convex projective domains. So that's a subset of the real projective space. So the projectivization of the real vector space of dimension d+1. And our requirements for this model set, for this model domain, are that it is open, that it's properly contained in an affine chart, and it's convex in such a chart. Okay, so the second requirement here is equivalent to saying that your domain omega does not contain an RP1. So it doesn't wrap all the way around the projective space. And then once you know that, once you have an affine chart, you can say that it's convex in such a domain. Okay, so I want to draw you some examples. So this could be an ellipsoid. So I'm going to draw a lot of pictures in RP2 because that's the dimension that I can draw pictures in. So if I have an ellipsoid, or a perfect ball inside of any other RPD, then in fact, this is going to be the projective model of the real hyperbolic space. So this is a generalization of hyperbolic geometry. We could also have, and we're going to come back to these examples and talk about them a little more. There's also the simplex. So this is the interior of the convex hull of d+1 points. So in dimension 2, that's a triangle. In dimension 3, that's a 3 simplex. And in general, we get the simplex of whatever dimension you want. And that also has sort of a special place in this theory, and we'll talk about it in a moment. But I want to also draw sort of just a generic example because these two are sort of misleading because they're very homogeneous. So in general, these are just sort of any kind of convex blob inside of the projective space. Shouldn't expect them to have any projective automorphisms at all, but of course, those that do will be interesting. Okay, so the second definition that we need is, so we want to think of these as, sorry, I'm working with new technology here. We want to think about these as projective spaces with a projective structure. So the natural group to think about is this automorphism group, the set of projective automorphisms preserving the domain. So this PGL is the natural group to act on the projective space, and we're just looking at the stabilizer of omega here. And these are the automorphisms of omega as a projective domain. And of course, we like manifolds. Compact manifolds are particularly nice, right? So we're going to be particularly interested in the domains that admit quotients to compact manifolds. So we'll say that if we can find a subgroup gamma, oh my gosh. If we can find a subgroup gamma of auto omega, which is discrete and co-compact, we'll say that omega is divisible and gamma divides omega. And so omega in this context is actually a proper metric space. So the remark is that requiring that gamma is discrete actually implies that the quotient gamma mod omega is a manifold. And that's sort of a lie, right? So this is actually just virtually a manifold. Gamma could definitely have torsion, in which case we get an orbifold, but we're working in a linear setting, so we can throw Selberg's lemma at it and get a finite cover that's a manifold. So this really is the right context to think about these are really the right words to think about manifolds that have this nice type of convex structure, of projective structure. Okay, and of course the implicit definition is that if we have a manifold that is realized in such a way, so if you can find a diffeomorphism from your favorite manifold to a quotient of such an omega by compact group, co-compact discrete group gamma, then we'll say that your manifold has a convex projective structure and is a convex projective manifold. Okay, so why should we study these domains? So I know that a lot of people are maybe not familiar with this type of geometry, but I think it is a really natural thing to think about with a lot of really beautiful properties. So I want to just tell you some of the nice results in the area. So this is sort of the sales pitch for convex projective geometry. So like I said, these are actually metric spaces. They're often negatively curved, but not always, in the sense of delta hyperbolicity. And we'll actually be talking about when that doesn't happen here. So at omega, the group of projective automorphisms of omega are acting by isometries. And the metric that is sort of natural to use from a projective point of view is called the Hilbert metric, which results from a projective invariant and the convexity of omega. So I don't want to dig too much into that, but I will say that no matter what, always the projective lines are geodesic. So if you draw a straight line in the projective sense, then you have drawn a geodesic inside of omega. Okay, and okay, and like I said, if you take an ellipsoid, then you have rediscovered the hyperbolic space in the sense of Klein, and so every hyperbolic manifold is also, every real hyperbolic manifold is also a convex projective manifold. But one of the nice aspects of the theory of convex projective manifolds is that you can actually do some deformation theory in dimensions beyond 2. So, right, in dimension greater than 2, when you're doing hyperbolic geometry, one of your big tools is the rigidity theorems, the Mostow-Prasad rigidity theorems. But as projective manifold, there's no reason that a hyperbolic manifold should be rigid in that sense. And in fact, we can do lots of interesting deformation theory. And it's not completely well understood when manifolds are projectively rigid. And that's a thing that people study and is pretty interesting. And also, these manifolds are not always strictly negatively curved. There's a lot of flat substructures that can happen in this context. And we're going to be talking about one aspect of that phenomenon in this talk. Okay. The third part I want to point out is that this is not just deformation theory of hyperbolic geometry. There are compact convex projective manifolds which support no constant curvature Riemannian metrics. So Kapovich showed this of infinite families of the Gromov-Thurston manifolds, which are also used to sort of demonstrate that maybe geometrization in the sense of Thurston doesn't necessarily work in dimension 4 or higher. But many of those manifolds do support convex projective structures. And yeah, okay. And the fourth point here is a little bit technical, but I think is a really interesting selling point. So if you look at the set of holonomies of convex projective structures on your favorite manifold, let's suppose it has some, then, and you start deforming them within SLD plus 1R, then and you ask which of those representations are holonomies of convex projective structures on your compact manifold, then the answer is that it's a union of collected components. So Kouzul showed that you can always deform a little bit inside of that space, and Benoist showed that in fact you can deform as far as you want, as long as it's still a faithful representation. So you get these nice open connected, connected components that are described very well as holonomies of convex projective manifolds, which is always a nice thing. So if you're interested in SLD plus 1R character varieties or moduli spaces, that's a nice selling point. And I want to just say that in the case where you have a surface, a hyperbolic surface, right, then this is the Hitchin component. So the space of convex projective structures on a surface is exactly the SL3 Hitchin component, which is a 16G minus 16 dimensional ball, and the Teichmuller space sits in there. And this is a thing that's sort of nicely studied by Choi and Goldman and Fakh-Gonchav and some other folks. But I just wanted to point that out because that's a very popular object, and this is sort of a nice way to understand it, at least for me. Okay, so that's my sales pitch, and I'll move on to the talk now. Okay, so right, I want to now talk about what the flat substructures are in this context. So, and the theme will be that the simplex is actually a flat manifold, and I'll say exactly what I mean by that momentarily. So let's return to this example where we look at delta K, the simplex, which is the interior of the hull of K plus 1 points in RPK, I guess. So this is a proper convex domain. It's contained in one chart. And so the audience participation part of the talk is to determine what the projective automorphisms of this domain are. So what are the points inside of this? Inside of the simplex, they are the classes of vectors that can be represented with only positive entries. Okay, so your job is to think about what are some matrices that preserve the fact that a vector has only positive entries. And this is maybe harder over Zoom, so I'll just tell you. But of course, you can take the diagonal matrices with positive entries, and those preserve the fact that your matrix has positive entries, and those are sitting actually in a semi-direct product with the permutation matrices. Right, you can permute those vertices of the simplex, okay? And that gives you an RK semi-direct, the symmetric group SK plus 1, okay? And I'm belaboring this because you should look at that group and sort of feel familiar about it, because it looks a lot like the translation subgroup of the Euclidean transformation, the Euclidean isometry group, semi-direct, the point stabilizer, right? So this is the isometries of Euclidean space. So in fact, this is already a lot of information, because if I have a discrete subgroup of the automorphisms of the simplex, then it injects into the isometries of Euclidean space. Okay, so now all of the crystallographic group theory applies to it, right? So in particular, this tells you by a theorem of Bieber Box that if gamma acts on the simplex and is dividing, right, meaning it has compact quotient and is discrete, then gamma by delta K is homeomorphic to the K torus, virtually. I'll put a V there for virtually. Okay, so we know quite a lot about crystallographic groups as long as you're willing to take things up to finite index. So this is really this is a flat manifold, at least from the perspective of group theory. And in fact, this the metric mentioned earlier actually induces this injection by Lipschitz equivalence. So it's actually by Lipschitz the Euclidean space as well, not only on this group theoretic level. Okay. So now the thing to consider is, okay, that's sort of the main theme here, is that a first perspective on convex projective geometry is maybe that it's a generalization of hyperbolic geometry where you can do interesting deformation theory to hyperbolic manifolds. But that's incomplete because there are also these aspects of flat geometry, of Euclidean geometry inside of convex projective geometry. So maybe there's a nice mix of flat and negatively curved geometry. Okay, so the thing to consider is that you could definitely have the following situation here, which is if you have your domain omega, your divisible domain omega, and you intersect it with some projective subspace of RPD, you could find that that intersection is projectively a simplex, right? So since we know that projective lines are geodesic, then in fact, this is a totally geodesic subspace that is flat, that looks like a Euclidean manifold. So these domains can admit subspaces that look flat without themselves being flat, being the simplex, right? So this is an interesting phenomenon. And so, yeah, right? I mean, compared to the hyperbolic space where every slice is a hyperbolic space of lower dimension. Okay, so this is sort of a new phenomenon. Okay, and so we'll borrow this definition here from Riemannian geometry. We'll say that a flat in a domain omega is a properly embedded simplex, where the properness is this property on the boundary, where the boundary of the simplex has to be sitting inside of the boundary of omega. Okay, and that is exactly enough to get that. That's what you need to say so that it's actually a totally geodesic subspace. Does it make sense? Okay. And for the rest of the talk, I want to say that I'm only going to discuss codimension 1 flats. So if I say flat, I probably mean codimension 1, though I'm going to try to be careful and say codimension 1. Okay. And so we're sort of inspired by the fact that in Riemannian geometry, you can really learn a lot about non-positively curved Riemannian manifolds by looking at their flat, totally geodesic subspaces. So especially those of low codimension, those of high dimension, are particularly useful in extracting topological data, in extracting group theoretic data about the fundamental group of the manifold. Okay. And in the context of convex projective geometry, there's a very nice result that is sort of celebrated and sort of got people re-interested in convex. So convex projective geometry, convex projective domains were studied sort of starting in the 1960s. And people learned a lot about them. And then they were maybe put down for a little while. But this person, Yves Benoist, kind of picked them back up again in the early 2000s and came out with a series of papers that they really got people re-interested in the subject in sort of a modern perspective. And this result that I'm going to tell you now is sort of something that really, really got people's attention, I think, and is I think, a really beautiful result. And inspired the work in this talk also. So the idea is that he took this work of Benzacri from the 1960s, who was studying convex projective domains sort of as a set, and which is amazing and confusing. But Benoist was able to show that if you have a divisible, irreducible convex projective domain in RP3, so we're talking about 3 manifolds, so we have a lot of extra tools, and we assume that it has some properly embedded triangles. So in this dimension, in dimension 3, the only interesting case for properly embedded simplices is those of dimension 2. So properly embedded triangles. So these are like copies of the Euclidean 2 space sitting inside of your domain. And this word irreducible, I'm going to just sort of hide under the table, but I'll tell you that it's sort of a natural indecomposability condition for the domain. Okay. And the result is that if you have an irreducible divisible domain in dimension 3 and it has properly embedded triangles in it, then in the quotient M, the triangles project exactly to the tori of a JSJ decomposition for the manifold, for the 3 manifold. And furthermore, the pieces in that decomposition are necessarily finite volume cusped hyperbolic manifolds, or rather are homeomorphic to finite volume cusped hyperbolic manifolds. So they're definitely not geometrically hyperbolic because, well, for example, the holonomy at the cusp. So, so the point is that on each of these triangles, there's a z squared acting, stabilizing that triangle. And in the quotient, that gives you a torus. And the tori are exactly are all of the tori in the manifold and also make up a JSJ decomposition. And then the pieces are cusped hyperbolic manifolds. Okay, finite volume cusped hyperbolic manifolds amalgamated along their cusp cross sections, which are necessarily the tori. Okay, so this is a really beautiful result. People sometimes call this a geometric JSJ decomposition. And I think it sort of reignited people's interest in the study of convex projective domains in their own right, because it sort of demonstrated that there was something greater than just hyperbolic geometry going on. So this result uses explicitly a lot of 3 manifold stuff, which, you know, is available because you're in dimension 3, but it sort of raises a question, which is, you know, the goal of the talk, which is to try and generalize this result. So that it's not obvious what you generalize. So, you know, you in dimension greater than 3, then there are flats of all codimensions. There could be flats of all codimension. And, you know, should they all project to tori? Should the ones that are of low codimension, the high dimensional flats project to tori, and the low codimension, you know, segments, geodesics are sort of flats, you know, not really, but they're definitely not a discrete set like this. So where does that stop holding? But for today, I want to focus on the question where you ask about a d-dimensional convex projective domain with d-1 flats in it and try to extract data from those flats. Okay, so right, the sort of philosophical question is here, which is, well, which parts of this argument of Benoist's result from the geometrization or the fact that you're in dimension 3, which is sort of restrictive on the fundamental group and, you know, other considerations for the manifold. Okay, and we'll discuss in a moment a little bit more about, you know, how Benoist's argument sort of goes. So maybe I should ask if anybody has questions before we go into the sort of details of this theorem. It would be a great time to ask them.
Yes, I have a question to the previous result. What if there are no triangles? Is the manifold hyperbolic?
Yes, the manifold is then hyperbolic. It is not necessarily, so so if there's no triangles, then by sort of geometrization arguments, it has to be a hyperbolic manifold. You can see immediately from some of Benoist's work that there's no tori in it, and the fundamental group is delta hyperbolic, which is a pretty good start. But however, the interesting thing is that it's not necessarily true that that convex projective structure is a deformation of the hyperbolic structure. They could be in different components of the SL4 moduli space of the fundamental group.
Okay, thank you.
Sure. Anybody else? Okay. Well, I will go on and tell you the theorem then, and then we can discuss how it works and ask some more questions later on. So, so the theorem is the following, which is a generalization of Benoist theorem. And so this is the part, these are the assumptions, just to be clear, and then the results begin after that. Okay, so the context is that we look at dimension d greater than 3, greater than equal to 3. If I do that, how does it look for you? Oh, it looks fine. And we take omega to be in the projective space, and we require it to be divisible, which is just saying that it has a manifold quotient, compact manifold quotient. And again, this word irreducible pops up. And maybe we can talk about that more later. But basically, let me just tell you, irreducibility for a convex divisible domain means that it is not built out of divisible domains of a lower dimension. So there's a way to put together a divisible k-dimensional domain and a divisible l-dimensional domain into a divisible k plus l plus 1 dimensional domain. And that thing has loads of flats in it and breaks the theorem, so we toss those. And of course, if you were studying such a thing, maybe a natural thing to do would be to break it into its constituent irreducible pieces and study those. Okay, so we start with such an object in an irreducible divisible domain, and we let gamma be a dividing group. So we should think of the quotient m, omega by gamma, as a manifold. It could be an orbifold, but up to finite index, it's a manifold. And I just want to name the projection P. So this is the natural quotient projection from the universal cover omega to the manifold M. And then the set we're interested in is the set F here of codimension 1 flats. And so this is the set of codimension 1 flats in omega. And we're going to assume part of the assumptions is that this is non-empty. If it's empty, the theorem is null, tells you nothing. So the result then is that if you look at the projection of the set of flats in the manifold M, it's a finite union of disjoint, incompressible, non-parallel codimension 1 tori, or virtual tori, where really you could say a little more here. They're not just virtual tori. These are homeomorphic to Euclidean manifolds. Go ahead. And are in fact, I guess, by Lipschitz to e to the d-1 manifolds. Okay, so this is much like Benoist's result. It tells you that it gives you a way to decompose your manifold into some constituent pieces that are amalgamated along their boundary. However, I want to point out this fact that there's really no reason that the constituent pieces, right? If I was going to draw you a cartoon of this theorem, it would be exactly the same as Benoist's cartoon, because I can't draw any dimension bigger than 3. But there's no reason to think in general that these manifolds should support hyperbolic structures. So what would such a thing look like? You can imagine such a thing even in dimension 4. So it would have 3 simplices sitting inside of it, and they necessarily form a discrete set because of the theorem, and then project to 3 tori. But in between those 3 simplices could be sitting 2 simplices, right? Could be sitting totally geodesic tori of dimension 2, so codimension 2 tori, and those would prevent the constituent pieces in this decomposition from ever supporting a hyperbolic structure. And those things a colleague tells me exist by playing with some Coxeter group stuff. So we should be open to that possibility. And what those pieces look like is an interesting question. And in general, not much is known about what you can say about, these are called cusped convex projective manifolds, which are a thing described by Cooper, Long, and Tillman, and classified by Ballast-Cooper. Well, the cusps are classified by Ballast-Cooper and Leitner. What the manifolds globally look like is not well understood. Okay, so that's the theorem. Is it clear? Okay. So I'm not going to go through the proof completely, but I want to sort of compare and contrast with Benoist techniques in dimension 3. And then maybe we can talk about some of the lemmas involved. So the idea from Benoist's proof is to think about the set F. So this, remember, the set of codimension 1 flats in your domain as a topological space in its own right. So, right, these are flats sitting inside of the projective space. So you can think of them, if you take them with their boundary, you can think of them as closed subsets of RPD. RPD is a topological space, and so this is a subset of the set of closed subsets, and so has a topology. And if you're not familiar with such a thing, the way that they converge is by all of the points in them converging. So a triangle converges to another triangle if all of the points in a sequence of triangles converges to that triangle. So it's pretty natural to think about. And my claim is here, which is that what we really would like to see is that the set of flats is a discrete set. So if we have that, yeah, the claim is that mostly the theorem follows from the fact that F is a discrete set. That's not obvious, so the work is to show it's discrete. Then if we knew it was discrete, we would know by the fact that P is a covering map that its image in M, a compact manifold, is also discrete. Okay, then we need to combine that with two facts. Firstly, this lovely fact from Benzacree in the 60s, which is that if we have two flats, if we have two codimension 1 flats in omega, they can't intersect unless omega is reducible. So this is due to irreducibility. Okay, so that's where that adjective appears.
Can anyone else see what Martin's writing, or is it just me?
Oh. No? Okay. Let me see. Can you see if I move the screen? Oh no, I'm frozen, aren't I? Okay. Let me just. Are we back? How's that?
Well, that's working for me at least.
Okay, great. Let me know if that happens again. I think if I don't do anything for too long, it freezes.
Okay.
Okay. Right. Okay, so where were we? So right, yeah, the claim is we want the set of flats to be a discrete set, because then what we'll do is we will combine that with this lovely Benzacree fact, which is that the irreducibility of omega tells you that flats actually can't intersect. The reason is that if they intersected, you have a co-compact group action, and you can use that to demonstrate that your domain is actually just a simplex, basically. And you consider the faces of this convex domain. You get codimension 1 faces, and then from there you can play around with the projective geometry to demonstrate that your domain is actually just a simplex, which is reducible. Simplices are reducible. And then once you have that flats can't intersect, you know from, this is a theorem called the Bieber Box Sol Theorem, which is basically saying that all Euclidean manifolds up to finite index are torus of some dimension cross R to the K. So they have some torus core, some compact core, which is a Euclidean manifold of lower dimension, which is virtually a torus, and then times just r, or r squared, or r cubed. And in terms of group theory, that's saying that if you have a discrete subgroup of the isometry group of the Euclidean space, then it's virtually free abelian. So, right, this then tells you, right, so then from there, we get most of the main theorem, because I claim that you actually know then that if you know this is a discrete set, then you know that you have finitely many compact images, that set F has finitely many compact Euclidean manifolds in M, because M is compact. If there were infinitely many, or if the images P of F were not compact, then they would accumulate somewhere in M. And you would see then, in an evenly covered neighborhood, you would see that accumulation in omega. Okay? And then if you know that, then you just consider what the stabilizer of those codimension 1 flats can be, and you know it's a discrete subgroup of the isometries of the Euclidean group, and you know that then your manifold must be virtually a compact, a torus, virtually a K torus, D-1 torus. Okay, so there's nothing fancy going on there after you know that F is discrete. Okay, so the point is that the goal is to show that the set script F of flats is topologically a discrete set, has no accumulations. Okay, so this is exactly where Benoist's theorem is a 3-manifold theorem. So what does Benoist say? He says, okay, well, I know from Benzacree that these flats can't intersect, so they can pile up on each other maybe, they can be discrete, but that sounds a lot like a lamination. So, and by like a lamination, I mean dual to an R tree. So, right, what's going on? Benoist says, here's omega, it has these triangles sitting in it. If I replace the spaces between the triangles with points and I replace the triangles with edges, then I get a thing that looks like a graph. And by looks like a graph, I mean is an R tree. And I also have a 3-manifold group acting on it. Okay, so there's knowledge about these things. So if you have a 3-manifold group, there's this, in particular, there's a theorem of Morgan and Shalin that says that if you have a 3-manifold group acting on an R tree, it either has a global fixed point or there's some edge that is stabilized. There are some edges that have stabilizers. Okay, and from there he starts to get some traction on this set of flats, and you know, that's the starting point at the very least. And using some projective geometry, then you can show that. So once you've created stabilizers for the flats, then they have to actually be isolated, and so that's the connection. And that's just some projective geometry stuff that is maybe a little tedious to show in a presentation. So, but I want to point this out because this is where Benoist's theorem is a 3-manifold theorem. This is the part that's 3-manifold stuff. So we need different methods, the general case, where the dimension might be greater than 3, because there's no obvious generalization for this theorem of Morgan and Shalin, right? In general, you know, there are some restrictions for how a group can act on an R tree, but nothing so stringent. So we need to do a little more work. And so what we do is we take some ideas. So Victor Schroeder in the 90s was working with non-positively curved Riemannian manifolds of finite volume, particularly those in dimensions 3, and 4, and was able to demonstrate some really strong results about the codimension 1 and 2 flats. In particular, the codimension 1 flats, he has a lot of really nice methods for, and we're able to, so the work was digging through those papers and figuring out how to adjust, how to generalize, how to make the lemmas and the theorems work in the projective setting. And so basically there are a couple of key ideas from there combined with really a lot of projective geometry facts to give sort of a more, so in particular we have a method of reproving the Benoist result in a more elementary way, but without this sort of sledgehammer of 3-manifold R-tree stuff. So a lot of that is sort of tedious projective geometry stuff, but I want to just demonstrate at least one of the useful tools from that context. So except for the case of the hyperbolic space, the ellipsoid as a convex projective domain, there's no reasonable choice for a Riemannian metric on omega. In particular, omegas that are not the simplex and are not the ellipsoid are not homogeneous spaces. So the metric at each point doesn't look the same. And so there's no real reasonable choice for Riemannian metric, which is a shame because Riemannian metrics are really nice. And one of the most useful tools is a normal direction, right? You can say, if you have a codimension 1 thing, you can say, the normal direction. But even in the case of non-Riemannian convex projective domains, in fact, flats always have preferred normal direction for irreducible divisible domains at the least. So let me just tell you how that works. So the idea is that you have your domain omega, and you have your properly embedded simplex. So I'm drawing in dimension 3 because it's the dimension you can draw.
I think it's frozen again.
Oh, man. So it is. Well, that's easy enough to fix, isn't it? Okay, there we go. So, right, so here's omega, and we have a properly embedded simplex sitting in there. This is a properly embedded triangle. And through the irreducibility, we know that each of these edges has a unique supporting hyperplane. So that's 1, 2, 3 supporting hyperplanes in RP3 in this case. And so the supporting hyperplanes have to intersect in a unique point outside of omega. So if this flat is called F, then we call this flat out here F hat. And if you're familiar with the projective model for the hyperbolic space, this is exactly the same construction that you do to get the dual point to a hyperplane. So this this point out here, F hat, is behaving like a dual point to this flat inside of omega. And what does that do for you? Well, it distinguishes for points inside of the flat X, it distinguishes a normal direction. So this direction is the normal to F at X. Okay? And you know, you could argue that this is sort of an arbitrary construction to do, but it also makes the lemmas work where you want there to be a normal direction to a flat. And that's why it's a good substitute. So this is really something sort of special in this context, that your flats have a distinguished normal direction. And so what this lets us do is it lets us start describing the behavior of nearby flats. In particular, you can say that if flats get within some epsilon of each other, then the normal to one has to intersect the other. And so this is sort of the start of, this is sort of your foothold into this geometry, because now you want, right, we're interested in how flats can accumulate. Well, now we can say something about what happens to flats as they get close. And this ends up being a pretty useful tool. Okay, so yeah, in summary, I just want to say that, yeah, sort of a more elementary technique that involves just mucking around in the projective space, reproves this theorem in dimension 3, most of this theorem in dimension 3, and gives a nice generalization and decomposition for divisible convex sets in higher dimension. Okay, I'll stop there. Thanks for listening. And Zoom talks just don't have sort of the excitement of a chalk talk today.
So are there any questions for Martin?
Yeah, please ask questions.
So, I mean, are there sort of good examples of these projective manifolds with your, flats in them and things?
Yeah, that's an interesting question, and I should say that omega divisible with codimension 1 flats, and I should say irreducible with codimension 1 flats are known to exist in dimension d less or equal to 7. So you can use Coxeter polytopes to construct these examples pretty easily. So these are reflection groups acting on polytopes, and you can construct examples pretty easily that have, Benoist actually did this in his 2006 paper, that have these AN subgroups, these triangle group subgroups that give you codimension 1 flats. But because of the combinatorial restrictions of Coxeter polytope groups, you can't do this in any obvious way beyond dimension 7. And I think maybe that's about as far as you can push it. It's not known whether they exist in dimension higher than 7. So my guess would be yes, but the methods are not, it's not obvious. So yeah, that's a really big question for me personally, is trying to make these things in arbitrary dimension. Hi, Steve.
I mean, I guess as you get into higher dimensions, you can't really visualize the projective domains. I mean, I guess somehow my imagination is these projective domains are kind of fractal-like somehow, or something.
Yeah, yeah, they're definitely fractals, but they're the Fuchsian group, Kleinian group people get the fun fractals that are in complex space. These are not that exciting looking because they all, they're all convex, so they just look like circles, but they are, in actuality, very complicated fractals with lots of interesting behavior at the boundary, but it's a little hard to see. Yeah.
Yeah. Are there any other questions, or should we thank Martin again? Okay, well, I guess we'll thank Martin again.
Thank you for inviting me.